So in this video, we're going to look at graphing logarithmic functions. And so a logarithmic function looks like f of x equals log base 2 of x. I want you to remember that this is effectively a y equals log base 2 of x. And we need to think about this in its exponential form. It'll help us graph it. So this is my log base. It's the base. That's the base of the exponent, 2. And remember that the answer in a log is the exponent there. And the x, in this case, the input for the log function, is actually the answer to the simplified version 2 to whatever power it is. And if we think about a log function in this particular form, it can help us make a table and understand why the graph takes the shape that it does. And so you have to remember, we have the input x and the output y, but the input is the answer and the output is the exponent we would need to get that value. So it's 2 to what power equals whatever y is. Whatever x is, 2 to the y power. So we're dealing with multiples of 2 because it's 2 to a certain power. It's 2 multiplied by itself a certain number of times. And so if I were to say the x value is 2, that means 2 to what power equals 2 to the power of 1. Well, if you remember from a previous video, we talked about when the bases are the same, the exponents are equal. So y equals 1. 2, 1. Now, if I were to say 4, the output right here is 4. 2 to some power equals 4. Well, hopefully you can remember that 2 squared equals 4, or that we could rewrite 4 as 2 to the power of 2, so y would have to be 2. Let's see here. If I had 8, 2 to the power of y equals 8, but 8 is 2 to the power of 3, so y would have to equal 3. And on this part, it's hopefully it's fairly intuitive. Let's start plotting those points. 2 to the power of 1, 4 to the power of 2, and 8 to the power of 3. And so you can see that there's a curve forming. But what happens when it's less than 2? Say, what happens if my output is 1? Oops, let me change colors back. What happens if I had 1 right here? If I can get this thing to right. So 2 to some power equals 1. Well, hopefully remember that any number to the 0 power is 1. So 1, an output of 1 means the exponent had to be 0. Now, that puts us 1, 0, that puts us right here. That's an x-intercept. What about for x values that are less than 1? So remember that we're still talking in multiples, powers of 2. So if I were to say 1/2, so 2 to some power equals 1/2. Well, hopefully it's not too big of a stretch to say that's -1 because that's a multiplicative inverse, -1. And if I said 1/4, that would be 1 over 2 squared, so that would be -2, and 1/8 would be -3, and hopefully you would see that there's symmetry, right? These are all mirrored. But what does that look like graphically? Well, graphically, we have x value of 1/2, and then -1, and then -2 and 1/4, and -3 and 1/8. And what you have is this curve coming and making a nice, neat asymptote right there along the y-axis. So question, what about all this stuff to the left of the y-axis, all those values that have, all those negative x values? And what's interesting is we can't actually have negative x value. If I said -2, I'm saying 2 to the power of y equals -2. Well, just remember, though, that when we put an exponent here, it doesn't change the sign of 2. We can multiply 2 by itself. We can do the multiplicative inverse like we did for these right here, but it never actually makes it negative. For that reason, we cannot have negative x values, negative input values. It just doesn't exist for this particular function. We can't have that. And so when we look at domain and range, I can have values. Similarly to negative values, it can also never be 0, because 2 to some power will never actually equal 0. There is no exponent I can put right there that will make this equal to 0. I can get really small, 1/2, 1/4, 1/8, 1/16, 1/32, so on. I can get real close to 0, but it'll never actually be 0. So when we look at the domain, you can see that there's a vertical asymptote right there at x equals 0, the y-axis. And so we have open parentheses, oops, I botched that, open parentheses, 0 gets infinitely close to 0 but never touches. That's why it's open, has this parentheses. And it will, in fact, go forever to the right. I can get values bigger and bigger. But the domain, and this is true not just for log base 2 of x, but if my function were log base 3 of x, or log base 4 of x, log base 5 of x, they're all going to take this same basic shape. The exact curve will vary slightly, but they will be this same shape. Now, when I look at range, well, this arrow right here is pointing down forever. So it goes down to negative infinity as it gets infinitely close to the y-axis. And this arrow right here, it's not as obvious, but what you have to notice is this is kind of going up at a diagonal, which means it's going up forever and it's going right forever. So my range goes from forever negative to forever positive, although it'll take a lot longer to get to forever infinitely high. But this is the domain and range for all log functions, log base 2 of x, log base 3 of x, log base 4 of x, etc. So, domain and range. Now, the last thing I'm going to say to this in graphing is that we can still do transformations. We can still do reflections over the x-axis, over the y-axis. We can shift up, we can shift down, we can shift left and right, and we can vertically and horizontally compress and stretch this. So all of our rules for transformation still apply. This is just a new parent function. This is a logarithmic function.